Morning, my dear students. Myself, Dr. Pichandi, Coordinator, School of Basic Engineering and Sciences from ESN College of Engineering and Technology. Today's topic is thermodynamics and heat transfer. So first, for a mechanical engineering student, as a part of some subjects, you have different streams. One stream is thermodynamics or thermal engineering stream. So this particular thermal engineering stream is very important for all the students and also for your future. That is, if you are going to attend any interview or you are going to attend any competitive examinations, you can have a more number of questions from thermal stream. So you should be very thorough with the basics of thermodynamics or thermal engineering. So this particular subject you can study from these subjects till 8th semester, and also this is very useful for you people. So first, what you should know, what is thermodynamics. So thermodynamics, it's a thermodynamics. You can split these things into two, thermo and dynamics. Thermo means you can convert this heat and energy. You can consider heat and energy. So the conversion of heat and energy or conversion from heat energy to the work energy. So work and heat, this is the most two things in thermodynamics. So the conversion from heat to work or work to heat. This is, so you have to study about these two properties, heat and work, in thermodynamics. So you have a basic energy principle, conservation of energy principle is used in thermodynamics. So if you see this boiler, this is a simple diagram. So in this simple diagram, you should know all the three things. One is boiler, you have a turbine and condenser, then you have a pump. So this is the simple diagram, and it is also called as Rankine cycle. So this particular cycle, how the heat energy is converted into work energy. So here the heat energy is supplied or received by the boiler and supplied to the turbine. So heat is converted, and this heat is supplied to the turbine. So you can get the work energy using this device called as turbine. So here the heat energy is converted into work energy. So this is also one best example for thermodynamics. So in thermodynamics you should know the basic things called as system, surroundings and boundary. This is a very simple and basic in thermodynamics. So first you should know what is system. So as a student, you are aware of this particular term systems. So wherever you go, you are telling that the system is very good, or somebody is telling that the system is not good. So why? So you know system is good or system is not good, but you should know what is system. So system means it's a quantity of matter. It's a matter in a space where your attention is focused to find out the thermodynamic property. Thermodynamic property. So for this is a small example. It's a system. Consider this is the system. So your attention is focused in this particular space, where what you are going to find out these things, you are going to find out the thermodynamic property of this system. So this is the quantity of matter where your attention is focused to find out the thermodynamic property is called as system. Suppose for example, you are in a classroom. So in your classroom, where is your attention means your attention is focused on the faculty. So your attention is focused to find out the thermodynamic property is called as system. Okay. Then surroundings. Surrounding means the mass or region outside this system is called as surrounding. This is the system. So outside this system is called as surrounding. Then you have one more term called as boundary. It's a imaginary surface, or you consider this as a real surface. It separates the system and surrounding. So this particular line, thick black line, is called as boundary. So you should know what is system, what is surrounding, what is boundary. System means it's a quantity of matter where your attention is focused to find out the property. Here, thermodynamic property. Then surrounding means the outside the region, outside this system is called as surrounding. Then this system and surrounding is separated by an imaginary or real surface called as boundary. So these three things is very important in thermodynamics. Okay, so thermodynamics, you should know what is system, what is surrounding, what is boundary. System is a quantity of matter where your attention is focused to find out the thermodynamic property. Then surrounding is the outside the system is called as surroundings. Then systems and surrounding is separated by an imaginary surface or real surface called as boundary. Okay. Then this system, you have a different types of system. So you should know what is system. In this system you have a different types. So different types of system. One is isolated system and the second one is open system. Then the third one is closed system. You have a isolated system, open system, closed system. So this slide shows you the isolated system. So in this system, it describes only two things. One is mass, another one is energy. So how much more? What about the mass? What about the energy? So system means you are considering two property. One is mass, another one is energy. So in this isolated system, mass or energy can cross the boundary of the system. No mass is crossed, no energy is crossed. So neither mass nor energy can cross the selected boundary. It is called as isolated system. So in the isolated system, mass is not crosses the boundary of the system. Energy also not crosses the boundary of the system. Some example. So as an engineer, as a mechanical engineer, you should know the example for each and everything. So this particular system called as isolated system, where neither mass nor energy can cross the boundary of the system. So example, day-to-day life example is coffee in a closed well insulated thermoflask. So you are keeping coffee inside the thermoflask. So here, what about the mass and energy? So mass, if it is closed, the quantity is not changed. Okay, so mass is not crosses the boundary of the system. If it is a insulated thermoflask, the heat energy should not be converts. So heat energy should not be passed to outside. So this particular example, coffee in a closed, well insulated thermoflask bottle, neither energy nor mass can be crossed this boundary of the system called as isolated system. Then the next one. So first we have seen the isolated system. Now what is closed system? So here also I already told to you, we are considering energy and mass. Okay. Suppose you can use this particular example. In this example, it's a closed system. It is called as closed system. This system, mass is constant. Mass is constant. So this mass is used to move this particular piston upward and downward. So the energy will be changed. Energy will be changed. So in this closed system, only energy crosses the boundary of the system. Mass is constant. Mass is constant. So closed system means only energy can cross the selected boundary. Mass never crosses the boundary of the system. So mass is constant. So this is called as closed system. The example for this one is tightly capped cup of coffee. Tightly capped cup of coffee. So previous one, the coffee is in a well insulated bottle, but here it is tightly capped cup of coffee. So this particular example, mass is constant, but what about the heat energy? So after some times the heat will be passed to outside, so heat energy will be crossing the boundary. Mass is not constant. This is called as closed system. Now the another type of system called as open system. Okay, so this open system, here both mass as well as the energy can cross the boundary of the system, called as open system. So in open system, mass is also crossing, energy is also crossing. Okay, crosses the boundary of the system, called as open system. What is the example for the same this open system? For the same cup of coffee, it is an open cup of coffee. So open cup means you can take this coffee. So coffee, mass of the coffee will be changed. Energy means that heat energy also changed. Suppose the first chip, the heat will be more. After some times, after 2-3 minutes, or after some times, the heat energy will be reduced. So this is called as open system. So you have the type of system, you have isolated system. Isolated system means neither energy nor mass can cross the selected boundary. Closed system, mass is constant, energy is crossing the boundary of the system. Open system, both mass and energy crosses the boundary of the system. Okay. So the example for an isolated system, coffee is in a well insulated thermoflask. So mass is constant, energy is also constant. Both the property never changes. So in this closed system, coffee is in a tightly capped cup. So mass is constant, energy is not constant. You can consider this one an open cup of coffee. The level of coffee will be changed and the heat energy is also changed. So this is the three different types of system. What are the three types of system? The first one is closed system, open system, isolated system. Okay. Then you should know what is the property of a system. So property, you have studied this particular term, properties, from your 10th standard. So property of a system is a measurable character. It's a measurable character. So what are all the things you are going to measure is called as property. Length, mass, so many things. What are things you are going to measure is called as measurable characteristics, is called as properties. So this particular property is subdivided into two things. One is intensive property and the other one is extensive property. Intensive property, extensive property. Intensive property means it is independent of mass, is called as intensive property. That is the property, it the mass is not considered. Okay, suppose the example, best example is temperature, pressure, density. So suppose you are in a classroom, the temperature is 33 degrees Celsius or 34 degrees Celsius. It is not changed, depends, it is independent on mass. Suppose the number of students is 20, the temperature is 34. Number of students is 40, the same temperature. So even though the mass is increased or decreased, this particular property never change. So this is independent on the amount of mass. The example, best example is temperature, pressure and density. Then just opposite, extensive property. Extensive property, it varies with mass. It dependent on the mass is called as extensive property. So volume is the example, energy is the example, enthalpy is the example. So these three things, volume, energy, enthalpy, this weight, these things will directly varies with mass. Suppose the mass is increased, what about the volume? Volume will change. Mass is changed, energy will be changed. Mass is changed, the property enthalpy will be changed. So you have a property means measurable characteristics. It is subdivided into two things. One is intensive and the other one is extensive. So intensive property means independent on mass. Example is temperature, pressure and density. Extensive property, it purely depends on mass. The example is volume, energy, enthalpy. Then property you know, but you have studied specific property. So specific property means nothing. It depends on it with respect to mass. With respect to unit mass is called as specific property. You know volume. Specific volume means with respect to unit mass. That is meter cube per kilogram. The volume, unit of volume is meter cube. With respect to unit mass, kilogram. Unit of mass is kilogram. So meter cube per kg is specific volume. Then you know energy, E. With respect to mass, that is energy. Unit of energy is joules. Joules per kilogram. So this is specific property. Any property with respect to mass is called as what? Specific property. The next one, what we have seen so far is, what are things we have seen so far? That is property, intensive property, extensive property we have seen. Then now you are going to study about state, equilibrium and process. State means it's a set of property that describes the condition of the system. Suppose you can use this particular example. It's state 1. State 1 means what are all the property? Mass. It is assuming that it is 2 kilogram mass. Temperature 20 degrees Celsius. Volume of this one will be 1.5 meter cube. Okay. So it's a set of properties describes the condition of the system. Suppose you consider this system. What about the system? Property of the system. Property of the system is it's a system having a mass of 2 kilogram with the temperature 20 degrees Celsius with volume 1.5 meter cube. It's state 1. Okay. So what is state? State means it's a set of properties which describes the condition of the system. Okay. Suppose if it is state 2. State 2, the property will be changed. Suppose if the volume here, the volume will be increased. Volume is 2.5 meter cube with this mass and temperature. So state 1, it describes this particular conditions. State 2 describe this particular property. Okay, so this is called as state. Then you should know what is equilibrium. Equilibrium means thermodynamic equilibrium. It is this system maintains thermal, mechanical, phase and chemical equilibrium. So thermally equilibrium, mechanically equilibrium and chemically equilibrium condition is called as equilibrium. Okay. Now process. So you should know what is state, what is equilibrium. Now what is process? Process means change from one equilibrium state to another. Okay, this is the process. Consider 1-2 is the process. 1-2 is the process. 1 is the initial state, 2 is the final stage. What about the property of state 1? V1. If it is P1 and P1, temperature T1. If you consider this particular state 2, volume is V2, pressure is P2 and temperature is T2. So change from property from one equilibrium condition to the another is called as process. Okay. So this process, you have a different types of process in thermodynamics. You have so many processes, that is isobaric process, isochoric process, isothermal process, adiabatic process, polytropic process, throttling process. Okay. So you have 6 process. So first we will see one by one. The first one is isobaric process. Isobaric process, it is also called as constant pressure process. Constant pressure process means throughout the process the pressure is constant. Suppose this is state 1, this is state 2, 1-2 is the process. 1-2 pressure will be constant. Pressure remains constant in this process. So it is called as constant pressure process. Assuming this is the PV diagram of a constant pressure process. Then isometric. It is constant volume process. Constant volume process, as you said, volume is constant. Assuming that this is process 1, the state 1, state 2. The process 1-2, what about the volume? Volume will be constant. What about pressure? This pressure is P1, this pressure is P2. So isometric or constant volume process, volume remains constant throughout the process, all other property will be changed. So this is called as constant volume process. Then you have a isothermal process. We will see these things in the next slide. Next you should know the thermodynamic processes. So in thermodynamic process, you have a cyclic process, reversible process, irreversible process. All the 3 is very much important for your calculation purpose throughout these thermal subjects. Okay. So cyclic system is nothing. When a system in a given initial state goes through various process and finally returns to its original state. Whatever may be the process, it goes with various processes, but finally it comes to the initial state. You have initial state 1. It's a one process. Okay, it's another process, but at the end of the process, it comes to the original state called as cyclic process. So cyclic process, initial state and final state equal. Final state and initial state will be equal, is called as cyclic process. Then reversible process. So in the topic itself, you should know what is reversible. It is a process once having take place, it can be reversed. It can be reversed. So in doing so, it leaves no change in the system or boundary. It's an important word. Once having take place, it can be reversed. It's called as reversible process. The next one is irreversible process. The process that cannot return both the system and surrounding to their original condition is called as irreversible process. You have a cyclic process, reversible process, irreversible process. Okay. So the last slide, what we have seen is three things. One is constant pressure process, constant volume process, and constant temperature process, isometric process. Next, we should know what is adiabatic process. Adiabatic process means there will be no heat transfer. There will be no heat transfer. It can be considered to be perfectly insulated one. So, no heat transfer take place in a adiabatic process. Then we have a isentropic process. In isentropic process, entropy remains constant. Isentropic process, entropy remains constant. Throughout the process, entropy is constant, is called as isentropic process. We have one more thing, polytropic process. Polytropic process, it follows the law PV power n equal to constant. PV power n equal to constant. It follows this law called as polytropic process. Then the next one is throttling process. In this process, no change in enthalpy, no work is done, and the process is called as throttling process. No change in enthalpy, no work is called as throttling process. Sudden expansion is also called as throttling, sudden expansion. So you have adiabatic process, isentropic, polytropic, throttling process. In addition to that, you have seen the constant pressure process, constant volume process, constant temperature process. So in thermodynamics, you have different types of process, depends on the property. If the property pressure is constant means constant pressure process. The volume is constant throughout the process means constant volume process. Throughout the process, temperature is constant means temperature constant, that is isothermal process. Then you have a adiabatic process, no heat transfer. No heat transfer. If entropy is constant means isentropic process. If this process follows PV power n equal to constant means polytropic. A sudden expansion process is called as throttling process. Okay. So these are all the basic things in thermodynamics. Then we will see the law of thermodynamics. Law of thermodynamics, you have a zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics. So first law of zeroth law of thermodynamics, it is considered only the equilibrium state. You consider A, B, C, that is you are seeing this A, B, C. A is a system, B is another system, C is another system, third system. Okay. So system A, B, C, all the three systems are thermally equilibrium. Okay. Suppose if two bodies are in thermally equilibrium with the third one, two systems A and B are thermally equilibrium with the third one. Third system is C. So suppose if it is happened, what is the next net solution means all the three systems are thermally equilibrium with each other. This is called as zeroth law of thermodynamics. So you have a three system A, B, C. All the three systems are thermally equilibrium. If two systems, system A and B is equilibrium with the third system C means all the three systems are equilibrium with each other is called as zeroth law of thermodynamics. Then you have a first law of thermodynamics. So first law of thermodynamics is nothing. It's in a cyclic process. It is a closed one system having a closed system, and you have a cyclic process. The net heat transfer and net work transfer equal to 0. So summation of heat transfer equal to summation of work transfer. What is the condition? Condition is system, it's a closed system and follows cyclic process. So first law of thermodynamics, it is applied to closed system and cyclic process. If a closed system goes through a cycle, the algebraic sum of total energy transfer is equal to work transfer. This is called as first law of thermodynamics. So zeroth law of thermodynamics, two systems are thermally equilibrium with the third one. All the three systems are equilibrium with each other is called as zeroth law of thermodynamics. First law of thermodynamics, if a system undergone a cyclic process, the net heat transfer equal to net work transfer, or subdivision. That is, if you consider these two things, it is equal to 0, called as first law of thermodynamics. Then what we are going to see is enthalpy. So enthalpy, it's a total energy of the system. What is the energy inside the system is called total energy of the system is called as enthalpy. So the total energy, you are considering two things. One is U, and the other one is PV, product of pressure and volume. Okay, U is the internal energy. U is the internal. Every system has its own internal energy. Okay. Then plus the product of PV is called as enthalpy. So specific enthalpy is considered this one. The energy unit of this enthalpy is kilojoules per kilogram. So enthalpy is a very important property. Throughout the study of this thermodynamics, you should know enthalpy. So enthalpy is the summation of internal energy and the product of PV. Okay. So this is some introduction about what we have seen is some introduction about the thermodynamics. Okay. The next one is introduction to heat transfer. Okay. What we have studied in thermodynamics is study of heat and work. Study of heat and work. Okay. So conversion from heat to work or work to heat is called as thermodynamics. It's a quantitative analysis. Then study of how heat flows, how much amount of heat will be transferred is called as heat transfer. It's a quantitative analysis. It's a study about how heat flows. How heat is flow is called as heat transfer. So heat transfer, heat is transferred from one place to another place or one area to another area. How heat is transferred? In heat transfer, what you are going to study is why heat is transferred. Why heat is to be transferred? Due to some problem, due to get some work energy or any energy, you need to transfer the heat. How heat is transferred? How heat is transferred means you have a different modes of heat transfer. Modes of heat transfer, you don't tell it's a type of heat transfer, it's a mode of heat transfer. You have three different modes of heat. Modes is used in heat transfer solution. The one is conduction. Conduction is one mode of heat transfer. Another one is convection, and the third one is radiation. So we will see one by one. The first one is conduction. The transfer of energy in a solid or fluid via molecular movement. Is called as conduction. Okay, you see this simple example. You have a pan. Inside the pan, you are having some fluid, whatever it may be. It may be a coffee or water or any fluid. So you can heat this particular pan. Okay, you can heat this vessel. So what happened if you are heating this vessel? What happened? This bottom of the vessel is heated. Bottom of the vessel is heated. Then this heat is transferred to the top of the vessel, top portion of the vessel. So this is called as conduction. Okay. So the conduction, what happens here is heat is transferred by the movement of molecules, by the movement of molecules, or by electron movements, molecular movement. So if you are heating this particular area, what happens? The molecular movement, that is electrons, this particular area, the electron will vibrate, it collides the next molecule. So heat is transferred from this molecule to the neighbor molecule, such a way that heat is transferred. So this is a mathematical equation. You consider before initial state of the temperature T0. Then after some times the temperature will be T1. So what about the difference T0 and T1? T0 will be more than T1. Then what about this one? This one will be the thickness. This one will be the thickness. Okay. So this heat conduction, what we are going to study is, you have to study about the heat transfer. So heat transfer with respect to area is called as heat flux. Respect to area is called as heat flux. So this heat flux is directly proportional to the temperature gradient. What is temperature gradient? Temperature difference with respect to distance. Temperature with respect to distance is called as temperature gradient. So heat flux is directly proportional to Tt by Tx. So you are going to remove this particular proportionality. So proportionality constant, if it is removed by proportionality called as minus K. K is the thermal conductivity. So Q equal to minus K into delta T divided by delta X is called as Fourier law of heat conduction. So heat conduction follows the law called Fourier law. Fourier law states that heat is directly proportional to heat transfer, not heat. Heat transfer is directly proportional to temperature gradient. Temperature gradient. So Qx equal to minus K delta T divided by delta X. Then you should know the thermal conductivity of several metals. For silver, this is the thermal conductivity. For gold, this is the thermal conductivity. Copper, this is thermal conductivity. Area, air, water. So thermal conductivity of this metal, thermal conductivity of this non-metal, the value is given in terms of watts per meter Kelvin. So the thermal conductivity unit is watt per meter Kelvin. That is watts meter inverse Kelvin inverse, watt per meter Kelvin. Okay. So this is a governing equation of steady state one dimensional heat conduction. You consider this is the plane wall. Consider this is the plane wall. In this, the initial temperature T equal to T1. At the other end, T equal to T2. That is, the temperature is T1 at one end, T2 at another end. Okay. What about the thickness? It's a 0. It's a L. Okay. So thickness is L. Thickness is L. Thermal conductivity of this particular material is K. Thermal conductivity is K. So what is Q? Q equal to temperature with respect to distance L. Temperature with respect to L. So Q is directly proportional to area, thermal conductivity, and the product of temperature difference divided by L. So this L divided by Ka, you can consider this as R, resistivity. So this resistivity is the ratio of L divided by the product of K into A. K into A. This is the governing equation for one-dimensional heat conduction. So this is initial temperature, final temperature. This is the thickness, conductivity, thermal conductivity of this surface is K. So Q equal to Ka delta T. Delta T means difference in temperature divided by L. So R equal to L by Ka. There is a plane wall. What we have seen here is the plane wall. The wall is made up of single material of thermal conductivity K. So Q equal to this one. We can find out the heat transfer rate using this formula. So in the simple problem, you will be given the thermal conductivity of this plane wall, initial temperature, final temperature, then thickness. Thickness of the wall is given to you. So if all the things is given, you can find out the heat transfer for a plane wall. So consider this is a composite wall. Composite wall. This is made up of 1, 2, 3. 3 different plane or 3 different surfaces. This surface is refractory lining 1 made up of refractory lining 1. This one made up of refractory lining 2. This one brick wall. Okay. So this particular furnace wall having 3 different wall, 3 different material consisting of 3 different materials, refractory lining 1, refractory lining 2, brick wall with the different thermal conductivity. So what about this thermal conductivity of this one? K1. Consider this as K2, this as K3. So K1, K2, K3. It's a thermal conductivity of 3 different surfaces. Then thickness. Thickness is, this is L1, L2, L3. Okay. Then temperature T1, T2, T3, T4. Here it's a ambient temperature. So are you able to know this composite medium consisting of 3 different wall having 3 different thermal conductivity with 3 different thicknesses. Okay. So this is another composite medium. It's a sphere. Inside this you have a cooling water. You have a tube wall and scale. It's a condensing medium of steam. It's another example for a composite medium. So in the composite medium, you should know what the governing equation. So I already told to you, it's a ambient temperature TA. Initial temperature of the first wall is T0, T1, T2, T3, and this temperature is TB. You consider this as TA, this as TB. Then temperature of inner wall T0, T1, T2, and the outer wall is T3. Okay. So here you have to find out the heat transfer rate. So heat transfer rate to be find out using this resistance. Using this resistance formula. So consider this one is RA, this is R1, R2, R3 and RB. Resistivity of this surface, resistivity of this wall, resistivity of the second one, resistivity of this one. Okay. So it is a Q, it is a heat transfer. You should know heat transfer through the resistance, all the resistance will be equal. Heat transfer through this resistance will be equal. All the resistance will be equal. So Q for this one equal to this. Equal to this. Okay. So consider TA minus T0 by RA equal to T0 minus T1 by RB, T1 minus T2 by R2, T2 by T3 by R3, T3 by TB by R3. What is RA? R is L by Ka. L by Ka. So here it's a no the heat convection, only no conduction, only convection takes place. So RA equal to 1 by HA into area. R1, this is the thickness of this wall L1, and area product and area multiplied with the thermal conductivity of the refractory lining 1. Thermal conductivity of refractory lining 2 is K2, this is K3. So R1 equal to L1 by K1A1, R2 equal to L2 by K2A2, R3 equal to L3 by K3A3. But area is common, area is equal, so this one. So finally you have a Q equal to difference in temperature, net difference temperature, net change in temperature Ta minus Tb divided by summation of this R, summation of this R. The unit is watt or kilowatt, watts or kilowatts. Okay, so this is also another example of this one. Here it's a second one is divided into 3 material, so you have to find out the equilibrium equivalent or it is multiplied, it is added with Re and Ra, you can get the net heat flow. It's a composite medium, it's a cylinder, you have a cylinder 1 surrounded by another cylinder, then one more cylinder, 3 things. Composite media, you have a thermal conductivity K1, K2, K3. So whatever it may be, Q equal to net heat transfer divided by R. Here R is R1, RA, R1, R2, R3, RB. So summation of all these 3 things equal to capital R. Then Ta minus Tb, net heat transfer divided by R equal to heat transfer rate. It is also denoted by the simple W. So you can get some problem in composite media. Composite cylinder, this is the formula. Composite wall, this is the formula. Composite wall, this is the formula. Only one thing is the value of R will be changed. Okay, so this is composite medium. This is a composite sphere. So what we have seen in a composite cylinder, composite ball, the same formula Q equal to Ta minus Tb divided by R. But R, the value of R will be changed. 1 by 4 pi K R1 minus R0 divided by R1 minus R2. So if you can go through the problem using this formula, it is very easy to find out the net heat transfer rate. Heat transfer rate for what? Composite medium, that is composite sphere, composite cylinder, composite wall. Okay, so the formula is the net heat transfer rate, difference in heat transfer divided by R. It's another thing is critical thickness of insulation. So insulation you have studied, I think you have studied from plus 2 itself. Plus 2 onwards you can know what about insulation and other things. So insulation, this cylinder and the outer cylinder is covered with an insulation, So convection into an ambient temperature, this is the height of the cylinder. So here the critical radius of insulation R. You have a graph between heat loss and insulation radius. This is the maximum. You are increasing the heat loss for a particular critical thickness of radiation, then it is decreased. So this is a critical thickness of insulation. So far we have studied about conduction. So conduction, what is the law followed? Fourier law is followed. Q equal to Ka delta T divided by L is a formula. Conduction. Okay, so conduction, you have a conduction through plane wall, conduction through composite wall, composite cylinder, composite sphere. Now convection. So convection, it is occurs in liquids and gases. Okay, so energy transfer between the surface and fluid is called as convection. Are you clear? Energy transfer between the surface and the surrounding fluid, or the fluid surrounded over the surface is called as convection. This is the example. One example. Suppose this is the vessel. Okay, consider this is the vessel. You can heat this vessel. Inside the vessel you have a fluid. You take this as water. Okay, so you are heating this vessel. The vessel is consisting of water. So after some times, what happens? You are feeling that the water is getting heated. So you can get some heat. You feel the water is getting heated. How this water is heated? It is the heat is heat transferred from this place to this place by means of convection. That is heat transfer between the surface. This is the surface, and the fluid moving over it is called as convection. Okay. Suppose you have a formula heat transfer Q equal to, or heat transfer is directly proportional to area and temperature difference. Heat transfer by convection is Q directly proportional to area and temperature difference. The proportional, you can remove this proportionality, you can include the constant called as H. So Q equal to HA delta T. What is this H? Convective heat transfer coefficient. Convective heat transfer coefficient. So Q equal to HA TW minus TA. TW means temperature of wall. TA means ambient temperature. Surface temperature, the temperature of the fluid moving over it is called as convection. What is the law followed in this convection is Newton's law of cooling. Newton's law of cooling. Newton's law of cooling states that heat transfer is directly proportional to area and temperature difference. So if you remove this proportionality, you can include H. So Q equal to HA TW minus TA. What is the unit of this one? Q is watts, A is meter square, temperature difference is watts, Kelvin. So what is H? H equal to Q divided by A into this value. So Q is watts divided by meter square Kelvin. Meter square Kelvin. Okay. So convection process, for I will tell you what is different types of convection in the later part. Okay. So the convection gases value is this one. For free convection, this one. Okay. So convection, you have a different types. One is forced convection. Another one is free convection. Next one, mixed convection. Convection with the phase change, you have a boiling and condensation. Okay. So this is the convection, and energy transfer in the form of electromagnetic waves. It's a one. You have a combined one. So this conduction and convection, considering, but most of the cases both both modes will be taken into account. So one mode of heat transfer is by conduction, another mode is convection. Both the things will be happen. Example is fins. So the characteristics number used here is Biot number. The Biot number equal to conductive resistance divided by convective resistance. So efficiency of the fin, Q fin divided by ideal heat transfer. Heat transfer by fin divided by ideal heat transfer, it's a fin efficiency. This is some examples for fin efficiency with respect to H. Okay. Then fin effectiveness. Effectiveness of fin is equal to Q with fin divided by Q without fins. Q with fins divided by Q without fins. Okay. Then this is the, I told to you, you have a convection heat transfer, different types. Forced convection, natural convection. Forced convection, heat transfer between the surface and the fluid by means of some external sources called as force. So by external sources means you are using pump or pump, centrifugal compressor, whatever it may be. It's by means of these external devices, heat will be transferred from the surface to the fluid is called as forced convection. Natural convection, without any external sources, heat will be transferred by means of density gradient. By means of density gradient is called as natural convection. Natural convection. So there is no need of medium for external media for natural convection. We have an external agency required to transfer heat is called as forced convection. Forced convection. Okay. So this is the modeling. Engineer's prime connection, rate of convection enables sizing of the equipment. So these things already we have seen. Q is directly proportional to area and temperature difference. Remove this proportionality. Q equal to HA into the difference in temperature. It's a general formula for convection. Okay. Then as we have seen in the conduction, this difference heat transfer equal to difference in temperature divided by resistance. Here also use this resistance. In conduction R equal to L divided by Ka. Here 1 divided by HA. Okay, this is the thermal resistance or for convective heat transfer. So this is a unit. I already told you watt per meter square Kelvin. Okay. So typical values for pre-convection. Here is this one. What is the unit? Unit is watts per meter square watts per meter square Kelvin. Watts per meter square Kelvin. So what we have seen is two different modes, conduction and convection. Then the third one called as radiation. So radiation, what is radiation? So this radiation, heat is transferred by means of electromagnetic waves, மின்காந்த அலைகள். Electromagnetic waves, through electromagnetic waves, heat is transferred from one place to another place is called as radiation. So radiation follows this particular law, Stefan-Boltzmann law. Stefan-Boltzmann law. Whereas conduction follows Fourier's law, convection Newton's law, radiation Stefan-Boltzmann law. So the emission power of a black body is directly proportional to fourth power of absolute temperature. Fourth power of absolute temperature. If you can remove this one, you have a sigma value. So sigma is Stefan-Boltzmann constant. Stefan-Boltzmann constant. This is an example for radiation. This is the example for radiation. It's a pan. Inside the pan, iron. Iron is melted. So if you are here, that is, suppose you will be away from this device 1 meter. For example, 1 meter away from this device. What happens? You can feel some heat waves. You are feeling heat waves. This is by means of electromagnetic waves. This is called as radiation. Heat radiation is emitted by all objects above absolute zero and travels in straight lines. So this is the formula. This sigma equal to Stefan-Boltzmann constant. The value of Stefan-Boltzmann constant is 5.67 into 10 power minus 8 watts per meter square Kelvin power 4. It's a Stefan-Boltzmann constant value. 5.67 into 10 raised to minus 8 watt per meter square Kelvin power 4. Okay, so this is about mode of heat transfer. The last mode, radiation. So in heat transfer, what are all the modes we have seen so far is conduction mode of heat transfer, convective mode of heat transfer, radiation mode of heat transfer. Conduction follows Fourier law, convection follows Newton's law, radiation you have many laws. Among one is Stephen Boltzmann law. The next one is what we have seen is heat transfer. Okay, so heat transfer means transfer of heat from one place to another or one area to another area called as heat transfer. What is the device used to transfer the heat? This is the device. The name of this name is called as heat exchangers. So heat exchanger means it's a device used to transfer the heat from one place to another place. So heat exchanger, we have different types of heat exchanger. Here one is parallel flow heat exchanger. Parallel flow heat exchanger. So exchange of heat between two different temperature fluid. Two different temperature fluid. It's outer area, it's a inner cell. One inner cell, inner tube, outer tube. So inner tube, one fluid. The temperature of the fluid is going. Fluid is moving from this place to that place. Then what happens? The another fluid moving from this place to that place. So what is the movement of the fluid? Suppose assuming that the hot fluid is inside this inner tube, cold fluid is moving in the outer tube. What about the movement of the fluid? Both the fluid, that is hot and cold fluid, hot, this is hot fluid, this is the cold fluid. The direction of both the fluid will be same. Hot fluid towards right, left to right. What about the cold fluid? It's also towards left to right. So the direction of both the fluid is same, called as parallel flow. Called as parallel flow. Are you clear? It's a hot fluid flowing inside the tube, cold fluid flowing outside the tube. So what happens here? The heat is exchanged from this fluid, hot fluid to the cold fluid, hot fluid to the cold fluid. But here the direction of both the fluid will be same in direction, from right, left direction to right is called as parallel flow. This is the temperature distribution diagram. This is the temperature distribution diagram. So hot fluid rejects the heat from T1 to T2. This is the hot fluid. It rejects the heat from T1 to T2. It's the inner temperature of hot fluid, outside temperature of the hot fluid. What about this one, small t, inside temperature of the hot fluid, outside temperature of the hot fluid. So what about the difference? Inside is low, outside is more. So what happens here? This hot fluid rejects the heat. This hot fluid rejects the heat. What about this one? This cold fluid absorbs the heat. It rejects the heat, it absorbs the heat. So this is called as parallel flow heat exchanger. Then we have a counter flow heat exchanger. In counter flow heat exchanger, the direction of both the fluid will not be same. It is opposite. It will be opposite. Is called as counter flow heat exchanger. So in the counter flow heat exchanger, what happens? The hot fluid rejects the heat from T inside to T outside. What about this one? Cold fluid also rejects the heat, since it is the T inside. So what about the direction of this one? Hot fluid direction is this one, cold fluid direction is opposite to this. So this is called as counter flow heat exchanger. Counter flow heat exchanger.